Good morning. Today we are going to discuss about admixtures. If you recall of what we talked in the first lecture, concrete is made up of 6 ingredients, namely cement, fine aggregate, coarse aggregate, water, chemical admixture and mineral admixture. And these two we are going to discuss in this lecture. Admixtures. We can't think of a engineered concrete if we don't use any admixtures in the concrete. So, if an engineered concrete is to be made, then it has to contain either a chemical admixture or a mineral admixture. Okay. What do you mean by admixture? Is either added during the making of concrete or after the making of concrete to modify the properties of the concrete either in the fresh state or in the hardened state. That is, if we want to make a change in the chemical properties or its hardened stage properties, physical properties, then these admixtures have to be added to the concrete. The properties can either be a setting time properties or its strength properties, and that depends upon what kind of admixtures we are adding to the concrete. So, these admixtures are mainly added to modify the concrete properties as we wish as per our requirements. And this admixtures is being mainly classified into chemical and mineral admixtures. And now we are going to discuss about this chemical admixtures. This chemical admixture can be a single chemical or a blend of chemicals combined together. Usually these chemicals are available in solutions. In that about 35 to 40% will be active chemicals and the amount added will be less than 5% of the cement. When this chemical admixture, that is this admixtures came into existence, when we started using these admixtures, this chemical admixture and mineral admixture came into existence by 1930s. That is, we call some chemical admixtures as plasticizers, superplasticizers or hyperplasticizers, and according to ASTM they are called as, these plasticizers are called as water reducing agents, superplasticizers as high range water reducing agents and hyperplasticizers as very high range water reducing admixtures. These plasticizers came into existence by 1930s, and in 1940s air entraining admixtures came into existence, and superplasticizers came in the year 1963 and hyperplasticizers in the year around 80s to 90s. And still in many countries, like developing countries like ours, we are not using all the available admixtures for making an concrete. And in developing countries like ours, we are not using all the available admixtures for making an engineered concrete. We are not using all the available admixtures in the market. And this chemical admixture can be classified as follows. How these chemical admixtures are being classified based on their usage. Either they can be used to accelerate or retard the hydration reaction, or it can be used as an dispersing admixtures, or it can be used to entrain the air, called as air entraining admixtures. This air entraining admixtures, what they do is they entrain the air within them, and these are mainly used in cold countries. We will discuss about this later. air entraining admixtures. And another classification is viscosity modifier, that is they change the viscosity of the water. And another classification is they can be used for corrosion inhibitors, that is they can be applied on surfaces and can be used as corrosion inhibitors. So this chemical admixture is being classified based on what purpose we are using them, either to create any interaction during the hydration reaction, or it is being used as a dispersing agent, or viscosity modifier, or as air entrainers, or corrosion inhibitors. And we are mainly concerned about the dispersing admixtures. We are going to discuss in detail about the dispersing admixtures. About 60% of the admixtures we are using are of dispersing admixtures. They belong to the category of dispersing admixtures, and in that we are concerned about plasticizers, super plasticizers, and third hyper plasticizers. And according to ASTM, this plasticizer, super plasticizer and hyperplasticizer can also be called as water reducing agents. Super plasticizers as high range water reducing agents, and hyperplasticizers as very high range water reducing agents. So nothing but they mean the same what we are telling as plasticizers, super plasticizers and hyperplasticizers. Now we are going to discuss about plasticizers. These plasticizers reduce the water content up to 12%, that is starting from 5% to 12%, they can reduce the water content in the concrete. These plasticizers can reduce water reduction from less. These plasticizers can reduce water reduction right from more than 5% and less than 12% in a concrete. That is, the main aim of using these plasticizers is to reduce the water content requirement in the concrete. These plasticizers can reduce water reduction in concrete by more than 5% and less than 12%. That is, with less available water, they can make the concrete much workable, easily workable in a plastic condition. With less amount of water, even though we can work with the concrete. That is the concept of using these admixtures, that is plasticizers in concrete. We can reduce the water content. With much water content, the strength aspect will be very low, but using the less water content, even though we can work with the concrete easily. For that purpose, we are mainly using these plasticizers. So they reduce the water content requirement for a concrete. That is, by reducing the water content, these plasticizers will play a role to make the concrete plastic. That is, more workability will be induced to the concrete. We will be discussing about the term workability in the later lectures. Now, workable is nothing but how much easily the concrete can be handled, that is called as workability. So these plasticizers will make the concrete workable. These plasticizers will make the concrete flowable, that is, we can work easily even when we are using less water content. the dosage requirement for this plasticizer is 0.2 to 0.6 percentage on cement. This plasticizer's dosage is around 0.2 to 0.6 percentage on cement. That is, we are replacing cement by this plasticizers by 0.2 to 0.6 percentage. This is the range. This is the optimum range in which we can replace the plasticizers with cement. This is the optimum range in which we can use the plasticizers in concrete. These plasticizers are mainly of lignosulfonates. This lignosulfonates mainly are being used in this plasticizers. This lignosulfonates are mainly used in plasticizers, and this plasticizers is applicable for low to medium slump concrete. Another term, slump, we'll be discussing this later. These are all comes under the term workability. So this plasticizer is used for low to medium slump concrete, and the chemical which is being used in this plasticizers are lignosulfonates, and the dosage requirement is 0.2 to 0.6 percentage on cement. Based on that cement, we are replacing 0.2 percentage or 0.3 percentage up to 0.6 percentage of cement will be replaced with this plasticizer. Next, super plasticizers. Here the term super plasticizer means it is doing more work when compared to plasticizer. There the plasticizers reduce the water content from 5% to 12%. Here the super plasticizers will reduce the water content from 12% to 30%. So this 12 to 30% of water reduction can be achieved when we are using these super plasticizers. Here the dosage is of 0.6 to 2% on cement. So there the dosage was around 0.2 to 0.6% on cement. Here for super plasticizers the dosage is on around 0.6 to 2% on cement. That is, if we use 300 kilogram of cement, the dosage content of super plasticizers will range from 1.8 to 2%, that is per meter cube. For meter cube of cement, the dosage requirement of super plasticizers will range from 1.8 to 2%. For a 300 kilogram of cement, the dosage requirement of super plasticizers will range from 1.8 to 6 kilogram of cement. That is, we will be replacing 1.8 kilogram of cement with this super plasticizers. This is the range. If we use 300 kilogram of cement, the dosage requirement will be around 1.8 to 6 kg of super plasticizers. This much amount, what I am telling is for per meter cube of concrete, this much amount will be replacing with super plasticizers, and based on this is based on the dosage percentage, 0.6 to 2% on cement. There for plasticizers it was around 0.2 to 0.6%. Now we are going to discuss about this super plasticizer types. There for plasticizers only lignosulfonates are available. Here for super plasticizers they are of synthetic type What are the synthetic types? First one is sulfonated polymers of naphthalene formaldehyde, SNF. Second, sulfonated polymers of melamine formaldehyde, SMF. And third one is polycarboxylic ethers. This polycarboxylic ethers belongs to hyperplasticizers. The superplasticizers are of synthetic types, and these superplasticizers are of synthetic type, namely sulfonated naphthalene formaldehyde and sulfonated melamine formaldehyde. And the third one is polycarboxylic ethers. They belong to hyperplasticizers. But we will be clubbing both the superplasticizers and hyperplasticizers. So, I have included the polycarboxylic ethers in this category. Now, we are going to discuss about the plasticizers. What the lignosulfonates? What is the structure of the lignosulfonates? What is the molecular weight? That things we will be discussing. So, now I will show you the structure of lignosulfonates. This is the structure of lignosulfonates, SO3 minus and Na plus, SO3 minus and Na plus, and this is the SO3 minus and Na plus. This is the structure of lignosulfonates. It is a polymer link, that is the structure will be repeating in for n number of units, that is called as a polymer. All these plasticizers, superplasticizers will be of a polymer type. So, in lignosulfonates, that is in plasticizers, the lignosulfonates will be a heavily cross-linked polymer chain. The polymer structure of lignosulfonates will be a heavily cross-linked microgel. Its molecular weight is around 2000 to 60,000. In plasticizers, the lignosulfonates are of polymer type. It is a heavily cross-linked microgel and its molecular weight is around 2000 to 60,000. And when these plasticizers is used in the concrete during the mixing, that Na plus and SO3 negative will get dissociated. That is, Na plus will leave the polymer link and it will get dissolved in the solution, giving a negative charge to the lignosulfonate group, and this negatively charged particle will get attached onto the cement particle. The mechanism we will be discussing later after seeing through the structure of SNF and SMF. The sulfonated naphthalene formaldehyde is obtained by sulfonating either petroleum or tar at high temperature. The SMFs, the sulfonated naphthalene formaldehyde structure is being shown. The molecular weight of SNF is 500 to 2500. Compared to plasticizers, its molecular weight is less, and this paves the way for better dispersion since more particles get absorbed to the cement surface. The structure shown here is a double ring and it is free to rotate. It can rotate in either direction. Here also we are having Na plus and SO3 minus. When this is being added into the concrete, this sodium metal gets dissolved in the solution, giving a negative charge to the particle. And for SMF, sulfonated melamine formaldehyde, the link is the polymer link is the same except replacing 3 nitrogens. And for sulfonated melamine formaldehyde, it is same as of SNF, but here the naphthalene ring is being replaced by melanin ring. The remaining everything is same as of SNF. Next is polycarboxylate ethers. It is also called as PC or combed polymer. So this superplasticizers, plasticizers, hyperplasticizers are nothing but they are made up of polymers, that is n number of links will be repeating, and how because of that links the dispersing action is being induced, we will be discussing in the mechanism part. Now we are just seeing about only the structure of the chemicals, how these chemicals will look like: lignosulfonates, SMF, SNF, polycarboxylic ethers. Now we are just looking about its chemical structure alone. In mechanism part, I will be telling you how this structure influences the dispersing action. This polycarboxylic ethers are called as PC or combed polymer. Here, when compared to plasticizers and superplasticizers, there we have seen only one polymer unit, but in polycarboxylic ethers we will be having a main chain polymer, and to that main chain polymer another link of polymer will get attached. So it is called by the name combed polymer. One polymer chain will be available and another polymer will be coming from the main link polymer. So that is so only it is being called as combed polymer. These carboxylates mainly come from the carboxylic acids, COOH. The carboxylates mainly come from carboxylic acids, COOH. Now let us see the structure of polycarboxylate ethers. In that, a main link polymer CH2, CH, COOH, and that H is being replaced by a metal, that is sodium, and apart from that we are having ethers, ROR. This combination is available in the last link, CH2, CH2O, ROR, esters. So the COOH, it is polycarboxylic, and this ROR ethers, polycarboxylic ethers. This is the main link polymer and this is the combed polymer which is being attached to the main link polymer. Till now we have discussed about the structure of polymers present in plasticizers, superplasticizers and hyperplasticizers. Plasticizers, lignosulfonates form the polymer chain. In superplasticizers, sulfonated naphthalene formaldehyde and melamine formaldehyde will form the polymer chain, and in hyperplasticizers, that is polycarboxylic ethers, the combed polymer, that is carboxylic ethers will form the main chain, and another hyperplasticizers, the carboxylic ethers will form the polymer link, and the ether group will be attached to the main link polymer. Now we will be discussing about mechanism of action. When we discussed about the hydration of cement, what we saw is the small sized cation is being combined to large sized anion, and to fill that spaces it is being affected to. Now we are discussing about mechanism of action. When we discussed about the hydration of cement, what we seen was the cement particles belong to a category of small sized anions being bonded to large sized cations, and to fill the in between spaces it readily gets attracted to water, and the spaces are being filled by water of crystallization. So, during our discussion in the last lecture, that is the hydration of cement, what we seen there is the cement particles belong to a category of small sized anion. In the hydration part, we have discussed that the cement particles belong to a category of small sized cations being bonded to large sized anions, and to fill the in between spaces, it's being readily attracted towards water. So, the cations are of positive charged particles, and this, when water is being added, the rheological characteristics of cement water paste is nothing but either attraction or repulsion of cement particles. How this attraction and repulsion takes place when water is being added to the concrete, that is called the mechanism of action. And before going into the mechanism of action, we have to remind what we talked of in the last lecture, that is during the hydration of cement, the small size cations are being bonded to large sized anions, and in between spaces are being filled up by water of crystallization, that is hydrates are being formed to fill up the spaces to achieve the desired packing density. And during the hydration reaction, we also came across the different types of forces, that is what CSH exhibits between them is nothing but van der Waals force. This van der Waals force are responsible for attraction, particle attraction, that is the two particles combine together because of this van der Waals force of action. But a cement particle being positive, that is the cation being positively charged, we know that positive and positive charged particles will repel. But even though the particles being of same nature gets repelled, during the initial stage, this van der Waals force will be predominant in the concrete, and that causes flocks. Even though our particles are of same charge, they get repelled from each other, but the initial stage of hydration, these van der Waals forces will be predominant and it won't leave the particles to separate, and that causes the flock, that is the particles will not be allowed to move because of the repulsion force, but instead of repulsion force they get attracted towards each other, and that is due to this van der Waals force. That is, during the initial stage this will be predominant in the concrete, and that causes the flock in the concrete, and our main aim is to break the flocks, or water should be available for all cement particles. The water which we are pouring into the concrete should be made available to all the cement particles to take part in hydration reaction, and to prevent that flock formation only we are using these dispersing admixtures. This flock should be dispersed, they should not get it together, get close, they should be repelled from each other, and that is the main reason we are using this dispersing admixtures. And how it's being done is, we have seen the structure of plasticizers, superplasticizers and hyperplasticizers. In that, SO3 minus and Na plus, that is the sodium gets dissolved into the solution, leaving a negative charge to the particle, and our cement particles are positive charged, and the dissociated metal from the polymer link will leave a negative charge to the polymer, and this polymer having a negative charge will get easily absorbed to the cement particle surface, giving a entire negative charge to the cement grains. So now the cement grains will have a negative charge and another cement grain will have a negative charge, and because of this negative charge they get repelled from each other. So the water will be available for all the cement particles to get hydrated, and this is the reason why we are using dispersing admixtures, and this is the reason why we are using dispersing admixtures in concrete. Now let's see a figure of how this dispersing action is taking place. First, the cement flocks. The first figure shows that how the cement particles are being flocked together, and after adding dispersing admixtures the particles are moving apart, and that creates the fluidity for the particles, and this is how the particles get apart from each other. This is a cement particle and this is another cement particle. The polymer is being attached, negative charge, they get repelled from each other, and the water available here will now be free, and so the other cement particles can get reacted with this water. In very high range water reducing admixtures, the dispersion action take place by the particle. In very high range water reducing agents, the dispersion action takes place by the separation of particle. It's being shown here. First polymer is being attached to the cement grain, and from that another polymer link is being available, and that causes further dispersion for the cement particles, and this is how the very high range water reducing admixtures will reduce the water content in a greater level. This is called as steric stabilization, steric effect. This is also known as steric effect. In very high range water reducing agents, the main polymer and another polymer is being like this, combed polymer. So this is a cement particle grain, and here another cement particle, here this polymer, and here this again this two cement particle will get dispersed to a greater extent, and this is called as steric stabilization or steric effect.